For the past few lessons, we've explored these polynomial quotient rings. They all have the form f bracket x, where f is a field such as z3, z7, or the reals r, mod an ideal generated by a single polynomial such as x squared, or x squared minus 1, or x squared plus 1. And we saw that the first two quotient rings on this list are not a field, but r bracket x mod bracket x squared plus 1 is a field, and that's because it's isomorphic to the field of complex numbers C. And here's the motivating question for today's lesson. Given a polynomial g of x, when is the quotient ring f bracket x mod bracket g of x, when is that a field and why? To answer that question, we have the following theorem. This theorem, which is in two parts, states let f be a field and fix a polynomial g of x in the polynomial ring f bracket x. Then part 1 says if g of x is factorable, then our quotient ring is not a field. Part 2 says if g of x is unfactorable, then the quotient ring is a field. Here's an example that illustrates the first part of the theorem. Let g of x be x squared minus 1 in z7 bracket x, where g of x factors as x plus 1 times x minus 1. And using this factorization, we can create zero divisors in the quotient ring. By multiplying the cosets, x plus 1 plus bracket g of x times x minus 1 plus bracket g of x, we obtain g of x plus bracket g of x. And that's because to multiply these cosets, we multiply their coset representatives, and their product is g of x. And g of x plus bracket g of x is the zero coset. And therefore, our quotient ring has zero divisors, and so it is not a field. And by generalizing from this example, we've already proved the first part of the theorem. And so let's put a check mark on this one right there. So the focus of today's lesson will be on the second part of this theorem. And here's an example that illustrates it. Let g of x be x squared plus 1 in r bracket x, which is unfactorable. And we saw in the previous lesson that the quotient ring r bracket x mod bracket g of x, or bracket x squared plus 1, is indeed a field. Today's goal is to prove this theorem. Fix a polynomial g of x in f bracket x, where f is a field. If g of x is unfactorable, then the corresponding quotient ring is a field. Now, until now, we've described many structural similarities between the ring of integers z and the polynomial ring f bracket x. For instance, both rings have the division algorithm. But now we will use these similarities to derive a proof of the above theorem. So let's begin by writing the above theorem about polynomials in the language of the integers. The analogous statement in z is the following. We start by fixing an integer p, so this is analogous to fixing a polynomial g of x. And then rather than saying if g of x is unfactorable in the integers, we would say if p is prime, then the corresponding quotient ring, z mod bracket p, is a field. And here, bracket p is the ideal containing all multiples of p. In other words, it's the familiar set pz. So in today's classwork, we will actually begin by proving the analogous statement about the integers. And then after that, we will translate the proof about the integers to prove our theorem about polynomials. That's the approach we will take today. Before we get started on the classwork, here's a quick review about cosets. Recall that two cosets can be equal even when their coset representatives are different. For instance, the coset 378 plus bracket 5 is equal to 3 plus bracket 5 because the difference of their coset representatives, namely 378 minus 3, which is equal to 375, is contained in the ideal bracket 5. And more generally, the coset alpha plus bracket p is equal to beta plus bracket p, where alpha and beta are integers. Those two cosets are equal if and only if the difference, alpha minus beta, is an element of bracket p. Analogously, in polynomial quotient rings, we can say the following. The coset alpha of x plus bracket g of x is equal to beta of x plus bracket g of x if and only if the difference of the coset representatives, namely alpha of x minus beta of x, is an element of the ideal bracket g of x. In other words, this difference is a multiple of the polynomial g of x. Now please pause the video and work on day 35 classwork, and afterwards we will review some of the problems and concepts. Once again, the goal of today's lesson was to prove the following theorem. Fix the polynomial g of x in f bracket x, where f is a field. If g of x is unfactorable, then the corresponding quotient ring is a field. And our strategy was to use the structural similarities between the ring of integers z and the polynomial ring f bracket x. The key ingredient to our proof is the GCD theorem, which was introduced very early in this course. And here's the version of the GCD theorem for the integers. If integers a and b are relatively prime, then there exist integers x and y such that ax plus by equals 1. And here's the analogous version of the GCD theorem for polynomials. If polynomials f of x and g of x are relatively prime, then there exist a pair of polynomials p of x and q of x such that f of x times p of x plus g of x times q of x equals 1. And as an added bonus, we now have enough background knowledge to finally prove the GCD theorem. But for that, please see chapter 35 reading for the proof of the GCD theorem for both integers and polynomials using the concept of ideals that we've been using. Here's the theorem. Fix a polynomial g of x in f bracket x, where f is a field. If g of x is unfactorable, then the corresponding quotient ring is a field. Now, as usual, we begin the proof by assuming our hypothesis. So assume that g of x is unfactorable. And our conclusion, that the quotient ring is a field, is written as the last line of the proof. To show that the quotient ring is a field, we must show that each non-zero element is a unit. In other words, it has a multiplicative inverse. So we let alpha of x be a polynomial such that the coset alpha of x plus bracket g of x is not the zero coset. In other words, this is a non-zero element of the quotient ring. And therefore, alpha of x is not contained in the ideal bracket g of x. And our goal is to show that the coset alpha of x plus bracket g of x has a multiplicative inverse. That will prove that our quotient ring is a field. Now the next step is where we use the assumption that g of x is unfactorable. And so here goes. Since alpha of x is not in bracket g of x, in other words, alpha of x is not a multiple of g of x, and since g of x is unfactorable, then alpha of x and g of x must be relatively prime. Then, by the GCD theorem for polynomials, there exists a pair of polynomials, p of x and q of x, such that alpha of x times p of x plus g of x times q of x equals 1. And we're going to use this equation to come up with a multiplicative inverse for the coset alpha of x plus bracket g of x. And hence we have the following coset product. Alpha of x plus bracket g of x times p of x plus bracket g of x, where p of x is the polynomial from this equation above. Well, by coset multiplication, that equals alpha of x times p of x, the product of coset representatives, plus bracket g of x. And we claim that this coset is equal to 1 plus bracket g of x, because if we rewrite this equation right here by subtracting 1 from both sides and then bringing this expression to the other side, we get that alpha of x times p of x minus 1 is equal to this expression, which is a multiple of g of x, hence contained in the ideal bracket g of x. That means as coset representatives, we can treat alpha of x times p of x and 1 to be the same, and therefore these cosets are equal to each other. And therefore we have the coset product alpha of x plus bracket g of x times p of x plus bracket g of x equals 1 plus bracket g of x. In other words, our coset, our original coset, has a multiplicative inverse, namely p of x plus bracket g of x. And therefore, our quotient ring must be a field. And that's the end of this proof, and also the end of this lesson. So I will see you next time.